Welcome. It's a pleasure to introduce one of our own here today, Wahlberger, who originally from Toronto in Canada and graduate both at Yale and Stanford, or from UNSW, where he's been here longer than I have. So I'm not sure how long. But anyway, he's going to talk on his current passion, which is rational trigonometry, I believe.
Well, thanks, Jonathan. So welcome, everyone. I'm Norman Wahlberger. I'm going to tell you today about triangle geometry. And we're going to be looking at some old, rather traditional aspects of triangle geometry. And then I'm going to introduce a very new development, which is triangle geometry in a hyperbolic geometry setting. Now, triangle geometry is an interesting subject. Of course, it has its roots back in antiquity. The Greeks knew some triangle geometry, and then in the 17th century it started to develop, and it's kind of gone up and down. In the 19th century there was quite a flurry of activity, which then resided a little bit, and then lately it's enjoyed a big renaissance. So there's a resurgence of interest in triangle geometry due to a number of things. One of them is the ubiquity of dynamic geometry packages that allow one to explore elementary geometry in a very hands-on way. I'm going to be using Geometry Sketchpad here today, but there's other ones that are available like GeoGebra and Cinderella and Cabri and CAR. Some of those are free if you want to play around. Okay, so a triangle is one of the most elementary concepts in mathematics. It's probably the mathematical object. Actually, it's probably the scientific object about which we know most about. So of all the objects in the world, I think it's fair to say we know more about a triangle than we know about anything else. And we probably know a lot more about a triangle than whatever is in second place. There's just a huge amount known. There's no way I can cover even a fraction of it, really. But I'm going to have a go at showing you some classical results that give you an idea of some of the developments in the subject. Okay, and probably a good place to start is the work of Desargues, the founder of projective geometry in the 17th century, who discovered a theorem that has the following consequence. So here's a triangle A1, A2, A3, and here's a generic point P. And from that point P, we can draw these three lines. They're usually called Savians or Chavians. And then we get this Chavian triangle here. And Desargues' theorem in this case tells us that these two triangles are perspective from a point. Namely, if your eye is at here, then the various corresponding vertices line up. And so these two triangles are also perspective from a line. And what that means is that if you draw the intersections of corresponding lines, for example, that one there and that one there, then you get one point of intersection. The intersection of this one gives you that one up there, and this one gives you that one up there, and then those 3 points are always collinear. Okay. So that means that if you have a fixed triangle and you think about moving this point P around, then you've got a canonical line that's moving around as well. That's an interesting, very elementary construction. Goes back basically to the 17th century. Now, something else that was discovered really from the first days are the fact that there are 3 special points in a triangle, well, at least 3. One is the orthocenter, which we'll call H, which is the meet of the 3 altitudes. Altitudes are just lines meeting the other side's perpendicularity. The centroid, which is the meet of the 3 medians. Those are the lines joining points to the midpoints of the opposite sides. And this one here, the circumcenter, is the meet of the 3 perpendicular bisectors. Those are the lines which are emanating from the midpoints perpendicular to the sides. So the fact that those triples of lines meet is already interesting in all 3 cases and was known to the ancient Greeks from antiquity. Remarkably, it was left for Euler, Leonhard Euler, the great mathematician of modern times, to discover that these 3 points are actually collinear. They lie on a line, which now, of course, is called the Euler line, and you can see it barely there in gray. And moreover, he realized that there was a ratio, that the ratio of this segment to this segment was always in the ratio of 1 to 2. And I'll just give you another configuration. So the points don't have to be inside the triangle. Here's a different triangle with the orthocenter. The intersection of the altitudes is down here. The centroid, the intersection of the medians is there. And the circumcenter, the intersection of the perpendicular bisectors is there. And you see that they're still collinear and they're in the ratio of 2 to 1. Now, there's a very nice explanation of why that's the case that I'll give you. So why is it that these three are collinear and why did they form this ratio? Well, the thing to realize is that a very elementary fact is that the centroid splits every median in the ratio of 2 to 1. That's a fact from elementary geometry. Okay. And that has the implication that if we dilate the big triangle, A1, A2, A3, by a certain factor, then we get this medial triangle, the triangle formed by the three midpoints. Now, how is that dilation accomplished? Well, if this is in the ratio of 2 to 1, then we should dilate by a factor of -0.5. Okay, so dilating by 2 means make everything bigger by a factor of 2. Dilating by 0.5 makes everything smaller by 0.5. Dilating by -1 would invert every point in the point of reflection. So by -0.5 means invert in the point of reflection and then shrink by a factor of 0.5. So that's going to take the big triangle to the medial triangle. And that dilation has the property that it preserves parallel lines. Lines which are parallel stay parallel. Lines which are perpendicular stay perpendicular. So what happens to these three altitudes meeting at H? Well, they go to the three altitudes of this one here. This is parallel to this from elementary geometry. So the fact that we have perpendicularity here means that we also have perpendicularity there. Which means that these lines are actually perpendicular bisectors of the big triangle. So that means that the reflection of H in G by this -0.5 dilation actually is that point there. Or to put it another way, the circumcenter of the big triangle is equal to the orthocenter of the medial triangle. So that's a proof of that celebrated result of Euler. Okay, there's another, well, there are many interesting points on the Euler line, but the next most interesting point is the center of the 9-point circle. So if you take the circle that goes through the three midpoints, this one right here, it turns out that its center is also on this Euler line. In fact, it's exactly halfway between the circumcenter and the orthocenter. In fact, that follows already from the discussion that we have already had. Once you realize that the circumcenter is in fact the center of the circle that goes through 3 points of the triangle. That's how you get the center of a circle through 3 points, is by drawing the perpendicular bisectors of the sides. Now, another interesting classical fact about the circumcircle, the circle through the 3 points, is that something called the Simpson line. So if you take a point, this little purple one up there, and you drop perpendiculars to the 3 sides of a triangle. So I'm dropping one perpendicular to get this point, another perpendicular to get that one, and then another perpendicular to get that one up there. Then if this point is on the circumcircle, then those 3 feet of the perpendiculars are collinear. Yeah, that's sort of if and only if. So collinearity of feet of perpendiculars, if and only if the point that you're starting with is on the circumcircle. Okay, and so this is called a Simpson line in honor of the fellow who discovered it. Or maybe there were a couple of people who discovered it. There usually are with many of these theorems. And here's an interesting thing that can happen that Geometer Sketchpad will generate very quickly for us. It's the locus of the Simpson line as the point that we're starting with in bigger and bigger purple now moves around the circle. And so this is one position, but if you move through all various positions, then this is sort of an envelope of this curve, which was studied by Steiner, a very important mathematician of the 19th century, and it's a so-called hypocycloid. It's also called a deltoid. It's a classical curve. And this is one of the interesting features about a triangle geometry, is that even though we're studying something very elementary, it doesn't take too long for interesting, more advanced things to start creeping in, for higher dimensional curves, higher degree curves, and interesting additional features. Okay, here's another interesting direction of classical research having to do with another construction of the angle bisectors of a triangle. So if we have two sides of a triangle, say this one and this one, then we can find lines that make equal angles, or in rational trigonometry, which of course is much better, equal spreads. Okay? Then there are two such lines. There's that one and that one. And those lines meet, well, traditionally in this point here, which is called the incenter of the triangle. But in fact, they meet, in giving us 4 points, which I will call them all incenters, although the standard terminology is to call these x-centers, but I like to think of them all sort of in the same pot. So a triangle has 4 incenters, and they have the property that if you draw a circle which is tangent to one of the sides from that incenter, then it's tangent to the other side. The other sides. So that means that's the way you get circles inscribed in a triangle, is by finding the incenters first. And you can do that not just in here, but you can also do it from here, and then you get another triangle which is in some sense inscribed in the 3 lines of the triangle. It's actually outside, but it's still touching the 3 lines of the triangle. And there are 4 such in the circles, you might say. Okay, and now we come to one of the most celebrated results in geometry, Feuerbach's theorem, okay, which connects these 4 incircles that we've just found to the 9-point circle that we talked about previously. That was the circle going through the 3 midpoints. So that's the circle in blue. It goes through the midpoint there, the midpoint there, the midpoint up there. And the theorem is that this circle is tangent to each of the 4 incircles. So these two circles are like 2 coins that are touching adjacent. So it just winds its way in there. It's tangent to this one, tangent to all 4 incircles. A beautiful fact. Not that easy to prove. There are a whole host of additional constructs. Let me show you something associated with the incircles and the incenters. So if we look at one of these incircles, say that one there, it touches they touch the sides in these 3 points. Let's call them contact points. And if we connect those contact points with the corresponding vertices, we get 3 lines which meet in a new point. That point's called a Gergonne point, in honor of the person who discovered it. So for example, here's another Gergonne point where we take the 3 contact points of this circle and join it with the corresponding vertices. So there are 4 Gergonne points. Now, in the last half of the 19th century, triangle geometry enjoyed a really dynamic period of development, as a lot of amateurs became really enthusiastic about the subject, and high school teachers played a prominent role in making lots of discoveries. And there were a few key sort of facts that really opened up new areas of research, and this is one of them, the discovery that there was such a thing called isogonal conjugates. So how does this work? So the isogonal conjugate of this black point is the white point, and the isogonal conjugate of the white point is the black point. How do we go from one to the other? Well, these brownish lines that I've got here, they are the bylines, the angle bisectors that are used for the incenters. Okay, so they're meeting in an in-center there, but we don't care about the in-center. We just care about these lines. I call them bylines. Now what we do is we join, say, this black point to the three vertices, giving us three Chavian lines. And we reflect each Chavian line in the corresponding angle bisector. So we reflect this line in this line to get this line. Similarly, we reflect this line in this line to get this line. And we reflect this line in this line to get this line. And those three reflected lines, which are in the light blue, lo and behold, meet. They meet in a new point, which is called the isogonal conjugate of the black one. And because only reflections are involved, kind of obviously, if you do it twice, you get back to where you started. So this means that if you've discovered an important point of the triangle, you can create another point by taking its isogonal conjugate. Then it was discovered there was another similar kind of transform called an isotomic conjugate, where what we do is we start with, say, the black one, and we draw the three Chavians, and now we use the midpoints of the three sides. What we do is we take this Chavian and see where it intersects this line, and we reflect this point in the median. Okay, we do that in all three places, reflect and reflect up there, and then we join these points to the corresponding vertices, and lo and behold, those three lines meet. And that's called the isotomic conjugate of the black one. And again, it's an involution in the sense that if you do it twice, you get back to where you started. Now, if you have something like Geometry or Sketchpad, and you can program pretty easily your computer to find these things, and then you can play fun games. And this is a particular, this is not a classical result. This is just a sort of an amateur investigation that I've made. Okay? I haven't come to any conclusions. No doubt somebody out there knows it or discovered it a long time ago, but anyway, I think it's sort of interesting. So you start with the point, the black one, and you can take isogonal conjugate or isotomic conjugate. So suppose you do both. Okay, so you take both, you do both conjugates. And then you decide to do both conjugates of those two. Well, one of them is going to give you back the point you started, but the other one is going to give you a new point. So you're going to get two new points. And then you do the isotomic isogonal conjugates of both of them, you're going to get two new points. And if you keep doing that, you start seeing that the points that you get start forming a pattern. They start appearing like they want to be on a necklace. They kind of bounce around from there are these two necklaces, and they kind of bounce around from one necklace to another. And it certainly appears that these necklaces are drifting towards these two vertices, A1 and A3. And maybe it looks like they're conics. Okay, so you move the black point around a little bit, and it's maybe still sort of conic shape, but it's not entirely clear. And then we can move the point outside the triangle. We can still do isogonal conjugates and isotomic conjugates. We get something different. It seems pretty clear that these are not conjugates, but I don't really know what these curves are. Okay, so if you feel like doing a little investigation, and let me know what these curves are. Another curious feature of this is that why do all these necklaces drift towards A1 and A3 and not A1 and A2? There's something special about those 2 points as far as this triangle is concerned. So it turns out in my experimentation anyway that no matter where I move this point, these necklaces are always drifting towards A1 and A3. Okay, so it seems interesting to play around and figure out what's going on there. Okay, so now I'm going to shift gears and move to hyperbolic geometry. So there are thousands and thousands of things known about Euclidean triangle geometry. There are relatively few things known about hyperbolic triangle geometry. Now, I'm not going to assume you know any hyperbolic geometry, so I'm going to have to kind of tread a certain path here, a minimal path to hyperbolic geometry. So hyperbolic geometry began in the 1830s with the work of Gauss, Lobachevsky, who's a Russian, and Bolyai, who was a Hungarian. And it was generally considered one of the important developments of 19th century mathematics. And models of it were first introduced by Beltrami, and these days there are two models that are reasonably well known, the Beltrami-Klein or projective model and the Beltrami-Poincaré disk model. So these two pictures are taken from the Poincaré disk model. And very briefly what happens is this is a geometry that's taking place in the interior of the disk. The lines, the straight lines in this geometry, are arcs of circles, which have the property that they're perpendicular to the bounding circle. Okay? And there's sort of alternate versions of distance and angle, and the trigonometric laws look quite different, and lots of things are a little bit analogous to Euclidean geometry, but different. So the natural question is, what would happen to triangle geometry? So here's 3 points, A1, A2, A3, and here's the triangle formed by them. Does it make sense to talk about, say, altitudes? Yes, there's a notion of perpendicularity. In fact, it turns out that in this model, the angles are just the same as they are in the Euclidean model. So it's called a conformal model. So perpendicularity just looks like the usual perpendicularity. And you can see here that these three altitudes do meet in a point, which I've called O here, but it's really the orthocenter. And there's a notion of midpoints, and the midpoints meet in a point called the circumcenter. So we're starting to get excited that now there's the possibility that maybe Euler's theorem is true. Maybe there's all kinds of analogs of Euclidean geometry in this hyperbolic setting. Unfortunately, one is quickly disappointed. Why? Because if you move these points around a little bit, you find something disturbing happening. If we moved the triangle so that it's now A1, A2, A3, so it's rather long and skinny, then the three altitudes are still these blue ones. There's one altitude, there's another, and there's a third. And those altitudes are not meeting. There is no orthocenter for that triangle. What about the perpendicular bisectors? Well, we can find midpoints as usual. We can draw perpendicular bisectors through those midpoints. Those are the red ones. And similarly, those red ones are not meeting either. So there's no circumcenter either. Okay, well, if you don't have a circumcenter and you don't have an orthocenter, then one is discouraged. And one suspects that perhaps triangle geometry doesn't work very well in this context. And that's largely been the attitude of mathematicians for the last 100 years. That hyperbolic geometry is great, but don't ask questions about triangle geometry because it probably doesn't work. There's been a few isolated things that have been discovered, but they're very isolated kinds of things. Okay, so there is a new theory of hyperbolic geometry. It's called universal hyperbolic geometry. So the history is that in 2005, I published a book called Divine Proportions, Rational Trigonometry to Universal Geometry, which outlines a new form of trigonometry. It's a much superior form of trigonometry to the one that you learn. Okay, so I can do all of your calculations much faster. I don't need a calculator. I can do it but with paper and pencil, and I can run circles around you if you don't have a calculator. Okay, so you can look at this book. You can look at my YouTube series. I have a whole YouTube series on rational trigonometry called Wild Trig. There's about 60 or 70 videos in that series so far. So there's plenty of evidence to support the statement I just made. But perhaps more interesting is that once you have rational trigonometry under your belt, so to speak, you can go to the hyperbolic setting and look at it from fresh eyes. And a new hyperbolic geometry emerges, which I call universal hyperbolic geometry. Okay, so here are a couple of papers that reference this. I'm going to be talking about something that's very relevant to this one. This should be number 3. I don't know why they're all number 1. That's number 1, that's number 2, that's number 3. Okay, number 3 is First Steps in Projective Triangle Geometry. It'll be published in COG shortly. But I also have a YouTube series called Univ Hype Geometry, Universal Hyperbolic Geometry, at my user, NJ Wildberger. And there's about 30 videos so far in that series that lay out this hyperbolic geometry in a nice way. And today I'm going to show you some of the possibilities that emerge with triangle geometry in this new setting. Okay, it's going to be a bit challenging because I don't have time to explain to you this new hyperbolic geometry, and I can't even assume that you know the old one. So I'm going to simplify things dramatically. Okay, I'm just going to use the bare essentials that what I need to create enough hyperbolic geometry that we can start seeing theorems. Okay, so the setting is the projective plane. So this is the projective plane. And all what you need to know is that there are also points at infinity. Okay, but you don't need to worry about that. That's a technicality. We're just talking about a plane, and there is a distinguished circle in that plane. That's always in blue, in the middle of our picture usually. Okay, that's what we're going to do hyperbolic geometry with. So hyperbolic geometry in simplified form is what you get when you start with an empty piece of paper and one circle. Okay, and that's all you need. Okay, and then you can start doing hyperbolic geometry. Okay, so and otherwise you don't need a compass. All you need is a straight edge. Okay, so you've drawn your circle once and for all, and now you have a pencil and a straight edge, and now we're going to do hyperbolic geometry. Okay, so what are we going to do? Well, I have to introduce the idea of polarity or duality, which defines perpendicularity. You have to get at perpendicularity first. Okay, and this is done by the most important property of a circle, in fact. Okay? The most important property of a circle is that it defines for you a correspondence between points and lines in the plane. Sadly, undergraduates don't learn projective geometry these days, so this kind of thing is maybe not familiar to you. Okay? But that's the most important property of a circle. That to a point, there is an associated line. And to a line, there's an associated point. So let me explain what that association is. So you start with any point in the plane. Let's call it little a. Here's what you do. You take any two lines through it that meet the circle. That somewhere they go cut the circle in altogether 4 places. And then you look at the diagonals of that quadrangle. You just join those 4 points in all possible ways. Well, that's one set of diagonals which we already have. And then you join these ones to get another point there. And then you join these ones to get that other point there. And then you take those other 2 diagonal points and you join them. You got a line. And remarkably, this does not depend on which 2 lines you drew through A. It only depends on A itself. So this is called the polar of A. A is called the pole of the line. This goes back to Apollonius, ancient Greek mathematician. Now, in the special case when A is outside, there's a sort of simpler way of doing this. A simpler way of doing it is just to draw the 2 tangents from A and draw the line connecting the 2 points of contact of the tangents. That's not quite as good a description because that only works if the point A is outside. The description I gave you works no matter where A is. Okay, so so for example here's a way of doing it with lines from A, cutting the circle, getting 4 points, and then drawing the full, all those 6 lines determined by those points, and getting this line here, which is the same line that we would be getting there. Okay, so, I should say, how do we use this to define perpendicularity? So we're going to define perpendicularity this way. We're going to say that 2 lines are perpendicular when one of them passes through the dual of the other. Okay, so I'm going to call this correspondence duality. So I'll talk about the dual of a point being a line, and the dual of a line being a point. So if I have 2 lines, if one of the lines goes through the dual of the other line, then we say that those 2 lines are perpendicular. So for example, the dual of this is this. So this line here is perpendicular to our red one. This one is also perpendicular. And that's all so far. So any line through this point is perpendicular to this line. And there's a duality, so that we can also define perpendicularity between points. We say that two points are perpendicular if one lies on the dual of the other. So, there's a duality in this theory. So for example, the dual of this is this line. This point lies on this line. This point C lies on this line. So we say that this point C and this point A are perpendicular. It's maybe a new idea because you're not used to perpendicular points in Euclidean geometry. But here there's a notion of perpendicular points. There's a notion of perpendicular lines. Okay, so the next dozen slides I'm going to present some geometry in this context, some triangle geometry, but it's not going to require anything more than this notion of perpendicularity. The first thing that we're going to talk about is the notion of an altitude. So the altitude from a point A to a line L. There's a point A, there's a line L. What would it mean to draw up an altitude? Well, it's got to be a line that's perpendicular to this red one. What does that mean? It means that it goes through the dual of the red point, the red line. This is the dual of that line. So the line connecting this to the point A is an altitude. Note that that construction is a ruler construction only. In Euclidean geometry, if you have a point and a line you want to drop an altitude, you need a compass. You can't just do it with a straight edge. You need a compass. But here, because we can find the dual of a line with a ruler and compass, with just a ruler, we can find altitudes just with our ruler. And I suppose I should remark that, okay, we found this altitude n, but it also has a dual, namely the little n. And so that's sort of another construction that's available. We can call this an altitude line. We could call that an altitude point. There's a special feature of this geometry, which is that there are certain points which are perpendicular to themselves. Okay. So what does that mean? So suppose that you imagine your point, let's say A, up at the top there. Its dual line is right here. Imagine what would happen if that point A started moving close to the circle itself. In that case, the point and the line would get closer and closer, and in the limit, you would get a situation like this, where the dual of this point is this line here, is the tangent. So this is a situation where a point lies on its dual, and so it's perpendicular to itself, because that was the criterion for being perpendicular, that it should lie on the dual of the point. So all the points on the circle are null points. All the lines tangent to the circle are null lines. And they play a role that's analogous somehow to null lines in special relativity, and there's a natural connection with this and relativistic geometry. Okay, so now let's have a triangle. Let's introduce a triangle. So we're only going to use a straight edge. This is not the Klein model. This is just a straight edge. We're doing geometry with only a circle in our plane, and we have our straight edge, and we have this notion of duality. So given this triangle, little a1, little a2, a3 in yellow, then the dual of this point is this line. This is outside, so the simple way of thinking about it is just we're drawing tangents. And where the tangents meet the circle, that's where we draw the dual line. Okay, so we've drawn the dual of that point is this line. The dual of that point is this line. And the dual of the A1 up there is the line A1 up at the top. So we get a new triangle, the triangle in light blue with points L1, L2, and L3. which is the dual of the original triangle. And pleasantly, if you do that again, you get back to where you started. So if you take the dual of this point, you get this line. And similarly for the other points. That's a consequence of the following important fact, that if A lies on the dual of B, then B lies on the dual of A. Okay, so now we can talk about the orthocenter, because we have a notion of altitudes. So we're going to use this triangle here, A1, A2, A3 in yellow, as a kind of a standard triangle for most of the rest of the talk. So I'm going to be talking about that triangle. So these lines in blue are the altitudes of that triangle. What does that mean? Well, for example, what does it mean for this to be the altitude to this line? It means that if we find the dual of this line, which I haven't shown you somewhere, but it's perhaps out here somewhere, then it's just the line joining this point to that dual point. That's how you find altitude. So if you do that for each of the 3 points, you get 3 different altitudes. And lo and behold, those 3 altitudes meet at a point, which we'll call the orthocenter. We'll use little letters to tell us this is hyperbolic geometry, not Euclidean geometry. Okay, we can do a few other things. We can talk about the dual of the orthocenter. That's the ortho line, H up there. We can also look at the base of the altitudes, B1, B2, and B3. And we can also find their duals. Generally in this subject, whenever you have an object, you should look at what does its dual look like. So the dual of B3 would be this line here. The dual of this one might be a line that's so far out over here that we can't see it. Okay, so once we have the orthocenter H, we get a remarkable line which we call the orthoaxis A. And here's what it looks like for this standard triangle that I'm going to be talking about. It's this line right here. And it's the line joining H and that point S up there, which is the ortho star. And I need to tell you, how do you find the ortho star from H? Well, we use Desargues' theorem. Okay, so if we think of the Chavians formed by the orthocenter H, they result in this Chavian triangle formed by the 3 bases. And we saw that Desargues' theorem tells us that corresponding lines from the original triangle and this triangle are going to be collinear. So if we join this one with this one, we get that point G3. And if we join this one with this one, we meet at G1. And we join this one with this line, we get G2. And indeed, G1, G2, G3 are collinear. That's just projective geometry. Has nothing to do with this hyperbolic setting. But what we can do now in this hyperbolic setting that we couldn't do before is we can take the dual of that line. Right? We can take the dual of this gray line, and that's that point S up there. And then you can join H with S, and that's the definition of the orthoaxis. And although it's early days in the subject, I claim that it's the most important line in hyperbolic triangle geometry. Okay, so here are some other interesting constructions. We're going to come back to the orthoaxis. I'm going to give you some evidence for why it's important. So hyperbolic geometry arose from a study of the parallel postulate from Euclid, and people trying to understand whether the parallel postulate was independent of the other axioms of geometry. So there was a lot of investigation about what does parallelism come down to in hyperbolic geometry. So from my point of view, the right way of thinking about parallelism is this, that in Euclidean geometry, say these two lines here are parallel because one of them is perpendicular to the perpendicular of the other. Okay, that's a sort of simple-minded local definition of parallel, which doesn't involve having to go out here forever and ever and check to see whether they meet or not. Okay, you can just draw a line that's perpendicular to one and see if it's perpendicular to the other. And if it is, you say their lines are parallel. Okay, so that definition is a very good definition for hyperbolic geometry, whereas the two lines meeting doesn't work because we're actually in projective space and any two lines meet. Okay, so what we're going to do is we're going to define parallelism in that way. And so what we can do is this. So we're starting with our triangle A1, A2, A3, still the same one. We've drawn our three altitudes in blue. Okay. So we know that this line here is perpendicular to A1, A3. So what we're going to do is we're going to construct a line through here which is perpendicular to that altitude. So this line is constructed by being perpendicular to that altitude. I remind you how you do that. You have to find the dual of this line, which is out there somewhere, and just connect this point with that dual point. You get that line, and we can now say that somehow this is some kind of parallel to this line through this point. And we can do that at each of the 3 points, getting this bigger triangle, which we call the double triangle of the original triangle. The double triangle of the original triangle. Okay, so now we come to a theorem. Okay. The theorem is that the double triangle and the original triangle are perspective. That means there is a common point when you draw corresponding lines. So this line, this point corresponds to that point up there. So if we draw the line joining them, then draw the line joining these, and draw the line joining those 3 lines meet at a point. And we'll call that point the double point or the X point of the original triangle. This is it's a non-trivial theorem. If you actually make the computation is quite extensive if you do it in sort of a naive way. Here's another theorem, that the double triangle and the dual triangle are perspective. Now where's the dual triangle? The dual triangle has, the dual of this point is this line, the dual of this point is this line here, and the dual of this thing is way up there somewhere. And the dual triangle is that gray piece. You see just part of that, the piece there. That's part of the dual triangle. And if I join corresponding points, if I join the D3 to the L3 and the D1 to the corresponding point in the dual, and also the other one where it is the D2 to the corresponding point, which is way up there somewhere, then those 3 lines meet at this point, which we'll call the Z point. And another point, the base center B, another important point, is obtained by doing what? Okay, so we start again with our little triangle, the orthic triangle formed by the feet of the altitudes. Each one of those sides has a dual. So we're looking at the dual of the orthic triangle. So for example, the dual of this line is that point C1 up there. The dual of this will be out here somewhere, and the dual of this will be down here somewhere, forming this triangle, which you only see part of, the orthic or the dual orthic triangle. And the claim is that that triangle and the original triangle are perspective. Means again, if you join corresponding vertices, the three lines that you create meet at a point, and there are the three lines in blue, and they meet at the point B. Okay, and now a rather remarkable thing, that the 5 points Z, B, X, H, and S that I've defined, they all lie on the orthoaxis. So the orthoaxis was by definition the line through H and the ortho star S. So the claim now is that these three new points that I've just defined, the X, Z, and B points, they all lie on this orthoaxis. And moreover, there's some harmonic ranges which will mean something only if you've learned some projective geometry. So Z, B, X, H, those are 4 points on a line. So there's a projective invariant called the cross ratio. And if the cross ratio is -1, then the points are called harmonic. It means that roughly that if in terms of distances, which is mostly familiar, that this point here divides these 2 points internally in the same ratio as this point divides them externally. So this to this equals this to this. Okay, so that's a harmonic range. And then also the points Z, B, H, and S. Z, B, H, and S are also harmonic, full harmonic range. Yes?
So obviously to get, don't you need to have an idea of length or something?
Say it again?
Don't you need to have a concept of length to get harmonic work?
No, not exactly. No, not really. It's purely a projective notion. It can be defined purely in terms of projective geometry. It is often presented as if it depends on a prior theory of length, but in fact it doesn't. That's the way. Okay, now I'm going to move up one step and introduce something else other than perpendicularity. I'm going to introduce two other concepts which are very important for triangle geometry. The idea of a midpoint of a side and an angle bisector. Okay, except I'm going to call them midpoints and bylines because angle bisector involves that dreaded word angle, which I hate. Okay, and bylines are shorter. Okay, so what's the midpoint? So here are 2 points B and C. I want to show you how to find their midpoints. And all what you're going to need is your straight edge. Okay, so you connect B and C to get a line. You find the dual of that line. You connect that point with B and C. You get 4 points on the circle. At least you do in this case. Then you take those 4 points and find their other 2 diagonal points. Just draw all possible lines, and you form this point as well as that point D up there. And it turns out that this and that are the midpoints of B and C. So there's a metrical notion floating around here called quadrants. There's an angular kind of replacement called spread, which come from rational trigonometry. I'm not telling you what those are. I'm just telling you this is how you construct the midpoint of a side. And there are in fact 2 of them. There are 2 of them. This is just another picture showing that the B and C don't have to be inside the circle. The same thing works if B and C are out there, for example, then D and E are the midpoints. The same picture actually shows how to bisect a vertex, by which I mean 2 lines. So if we think of M and N, if we have these 2 as our starting lines and we're interested in bisecting those 2 lines, we draw the same picture. We draw the M and N, take those 4 points, do these things, and then these 2 red lines are the bylines of that vertex. Okay, so we can take a triangle. And we can look at the bylines at each point. And we find that they meet, just like they do in the Euclidean case, in 4 points called the incenters. And we see that those bylines also meet the sides of the triangle in 6 points, which labeled A. I'm not sure if you can see them all. And I'm going to call those Apollonian points. So that's a theorem that those things are all concurrent. Okay, in Euclidean geometry, there's something called Apollonian circles. Let me just say briefly that there's a hyperbolic analog of those. There's conics called thaloids, which one can define. And these are pictures of the 3 thaloids. And then these, just as in the Euclidean case, these thaloids meet. The 3 Apollonian circles meet in 2 points called the isodynamic points. So I'm just pointing out there's nice conics floating around just as there is in Euclidean case. But these things are not quite circles, but they share some properties of circles. Here are some real circles. These are the incircles. So these are the analogs of the circles that are contained in the sides of the triangle, and their centers are the incenters. So that's a circle centered there. This turns out to be a circle centered here. In classical hyperbolic geometry, this is something that's called a curve of constant width. It's not usually regarded as a circle, but in this universal hyperbolic geometry, we see it as a circle. And there are 4 of them, and they touch the sides at these contact points, just as we had in the Euclidean case. Well, once we have those contact points, you may remember we looked at their Gergon points. What were they? Well, we had, say, let's see if we look at the incircle that was sitting here. It has that and that and that as a contact point. So if we join each of those points with the opposite vertex, then we get a Gergon point. And where is that? I guess that was the point there. So these 3 form that little brown one is their Gergon point, and there are 4 of them. There's one there, there's one there, and there's one there, and there's one there. One for every incircle. And now we can join the Gergon points with the associated incenters. There's 4 of each, and they're naturally in correspondence. And when we join them, miraculously, the 4 lines that we get meet in a point, and the point that they meet at is the Z point that I described to you earlier, what I call the double dual point. Here's a picture involving midpoints. So we have a triangle, and here are its 6 midpoints. There are 2 midpoints on every side, and we can draw perpendicular bisectors. And we get circumcenters, but we don't get just 1 circumcenter, we get 4 circumcenters. 1 there, 1 there, 1 there, and 1 up there. And I should also say that the midpoints are collinear, 3 at a time. So, for example, where can you see that? So along this line here, which is the dual of a circumcenter, goes through those 3 midpoints. There's a nice connection between these midpoints. And you expect circumcenters to be associated to circumcircles. I haven't told you what circles are, okay, but it turns out that there are such things, and here are the 4 circles that go through the vertices of this triangle. It's not 1 circle, there's 4 of them. And they have their centers at those circumcenters that I showed you. Okay, we can also talk about centroids. If you join midpoints to opposite sides, then the lines that you get should be called medians. And it turns out that they also meet, but you get 4 medians. I'm also calling them G, not to be confused with your Gergon points. There's 3 of them there, and there's a 4th one up there. So these are all theorems. The theorems are that these three lines are concurrent. And I'll just give you two more slides. This showing you sort of more things that happen. So if you happen to join the 4 incenters and the 4 circumcenters, you get 16 lines. And then remarkably, sort of these 16 lines generate 4 new points of intersection where 4 of them meet at a time, which one might call in-circ points. And if you join 4 incenters and the 4 centroids, you get 16 lines, and then you get those 16 lines meet 2 at a time at points on the actual lines themselves. So this is such a meet, and this is such a meet, and you get this. So these lines here are lines joining incenters and centroids, and they happen to meet these at this point here, and there are 8 of these along each line. Okay, so this is just a beginning to suggest that there's a lot of investigation to do. There's a lot of new discoveries waiting to be made by anybody who wants to discover lovely things. Geometer, sketchpad, and a little bit of patience, and you can, with relatively elementary starting point, you can discover lots of new things. So the references are, first of all, on Euclidean triangle geometry. One can't go past Clark Kimberling's monumental online Encyclopedia of Triangle Centers, which documents at least 3,000, maybe it's more now, different triangle centers that have been discovered. I've told you about maybe 5 or 6 of them, but there's actually thousands of them, and there's all kinds of wonderful relations between them, and it's just remarkable. There's a Yahoo group, Hyacinthos, which has been going for quite a while. Lots and lots of detailed discussion of triangle geometry. For the hyperbolic situation, well, again, my YouTube series, Universal Hyperbolic Geometry, had my user NJ Weilberger. And this is the actual correct title of that paper that will appear so shortly, which has a lot of these pictures and more in them. So I thank you for your patience and your attendance. Thanks.
Time for some questions. Question?
Yeah, I have a question.
Yeah.
Is there when you put up the midpoints in that slide with those 4 points, are they in? Is there cross ratio on one?
When we define the midpoints
Yeah.
up here.
Yeah.
Yes, this is a quadrangle, and it's a well-known fact that like these 4 points are harmonic, form a harmonic range. There's harmonic ranges floating around in this picture.
My next question is: have you looked at the area of these dual triangles and that sort of?
The area.
Yeah, the area of the triangle.
Well, area is a little bit of a problematic notion. There is a universal analog to area called quadria, but it behaves a little bit different from area. But it also plays an interesting role. But you have to think differently about area. Yes.
Just back to midpoint, actually. Why did you define them like this? Like, what's the analog? How's this analogous to the midpoints of Euclid?
Okay. Well, I haven't told you that there's a metrical definitions of how we measure in this geometry. So there's lots of formulas involving linear algebra that I could have written down. And then it's a theorem that with that definition of quadrants, which replaces length, this point actually is exactly has equal quadrants to these 2 points. But roughly analogous to this, you can think in terms of the Euclidean setting that if you have 2 points on a line and you think, well, there's usually just one midpoint, it's not entirely true. There's also a midpoint at infinity. Right? The point on the line which is infinitely far away is equal distance to the 2 points. And so if you're going to include that point on the line at infinity, which we do in this projective geometry, then there are 2 midpoints even in Euclidean geometry, in some sense. Okay, so you should think of it perhaps like that. And that's also a harmonic range, by the way. Yes.
Is there like a limiting case where this turns into Euclidean geometry?
Yeah, sure.
You make the circle big.
No, absolutely. Yeah. If you're just looking in a small little area there, and the circle is far away, then it all reduces to Euclidean geometry. And the things that if the things that are there are in your sight, then you get Euclidean theorems. Of course, a lot of the theorems I've talked about are things relating to duals, which will be very, very, very far away from you. But close to where you are, it'll be completely Euclidean looking. Any other questions? Yes?
This might be a weird question, but of all these results, do any proofs have a sort of purely geometric reasoning, or do a lot of them have to go back to the metric that you can find?
So the proofs of these is in a rather roundabout way. It turns out that if you just go to coordinates and try bashing, you quickly run into serious computational problems. It's not impossible, but the formulas become really intimidating. And so to prove these things, I do something rather different. I change my metric using fundamental theorem. I change coordinates, and so I end up introducing different metrical structures. Okay, so that simplifies the calculations dramatically, but it's a highly non-obvious kind of thing to do. But it's, yeah.
Just about drawing some pictures of the Poincare disk, and it didn't really work out very well.
Yeah.
Can you then translate this back to motions on the Poincare disk that look nice and easy to sort of handle?
Yeah, so when the things are visible in the Poincare model, then all the theorems that I'm showing you here today are true theorems in the Poincare model. And there's a sort of a standard way to go from the interior here to the interior of the Poincare model. It's just that, for example, the existence of orthocenters doesn't work in the Poincare model because in some of our pictures, even if the triangle's interior, the orthocenter will be exterior to the circle. So when you transform to the Poincare model, you will not see that point because it's lost, because it's outside the disk. But I could have shown you Poincare models of many of the theorems, or at least partial aspects of the theorems. You don't see the whole picture because you don't see the outside, but you will still see some things. Yes?
Do these results relate to or have any implications to other areas of mathematics? Like where do they fit in, I guess, in the bigger picture?
Well, I mean, hyperbolic geometry has lots of connections with lots of things. But I'd say the most compelling connection is with physics, with relativistic geometry. So it turns out that what we're doing here is really projective relativistic geometry. That would have been another point of view to take. In fact, you can go on YouTube, and I have a lecture called Hyperbolic Geometry is Projective Relativistic Geometry, which explains it from that relativistic point of view. Okay, so, and there's lots of nice group theory. There's some linear algebra floating around. There's lots of there's so much structure in here that you can find all kinds of things. If you're interested in whatever it is you're interested in, you can probably find it somewhere in this story. It's a very big and rich story. Yeah.
Is there like a parabolic version? I don't know, is there...
Yeah, you mean sort of parabolic as in...
Is there like Euclidean, hyperbolic, and some other one?
Yeah, that's a good question. There is. So there's sort of degenerate metrics. You can write these metrics down in terms of matrices, and then you can, instead of having a 1, 1, 1 on the diagonal, or 1, 1, minus 1, you can have 1, 1, 0. And that might be some kind of parabolic thing. It's a little bit degenerate, but some of the things will still work. But again, I probably should point out that everything that I've said here actually also works for spherical geometry.
Oh, yeah.
I should have mentioned that, okay? So if you want to do geometry on a sphere, it turns out that all the theorems that I've said here are theorems on the sphere as well. That's probably a good point to mention. It turns out to be independent of the metric, so it's really universal. It, in fact, works for any quadratic form, non-degenerate quadratic form.
There are no more questions. Let's thank Norman again for a very interesting